All right, I'm going to go through example number 2 for AP Skyview Chem Redox reaction, not an acidic solution. In this one, I'm going to go ahead and show you a couple things. First of all, we can write this in its net ionic form. So please recognize it might be easier for you to do that. This is aqueous, solid. This is actually liquid mercury. It's pretty cool. And aqueous. You just know this is a liquid because there are only two natural liquids, elements, bromine and mercury on the periodic table. So what is the net? You could find the oxidation states without doing the net, but you're going to see the net ionics often. So what you're going to see is this is actually Hg 2 plus, and then the nitrates, we're just going to go ahead and let those just float around. And this is solid iron, so you got some silver iron in here. And we have some liquid mercury forming, and liquid mercury is our only diatomic metal. It's kind of annoying, but it does that. And then what is this iron? Well, it's not solid anymore. It's aqueous. So what is its charge? This is 1 negative, so this must be 3 plus. So you've just assigned oxidation numbers by writing the net. That way, we don't have to deal with the nitrates at all when I go to balance this redox reaction. So that's a review on how to do nets and how we use them in single replacement when we do redox. Okay, so this sure made our job a lot easier. We know free uncombined elements are 0, so we're going to be able to figure out what's reduced here pretty easily now. 2 plus to 0, okay, so mercury, the ion, gets reduced to 0. So that means it must gain 2 electrons. All right, now I'm going to pause here. The reason I chose this problem is because you have to balance the reduced element. The reduced element here is mercury. So if we would have kept nitrate on here, we would have not worried about any of it. Just would have been going along for the ride. But this is going to be Hg2, and this is Hg, so I need a 2 here. What that does is it says you're not just gaining 2 electrons, you're actually gaining 4 electrons. So this is that step that kids have to be really careful. Before you move on to the next half reaction, balance a half reaction's atom that is oxidized or reduced, and then apply it to the electrons. Oxidized, we have iron, it's at 0, and it goes to iron 3 plus. So we have 3 electrons lost. Nice. And let's check it out. I have 1 iron and 1 iron. So I don't need any coefficients, and then I don't need to apply anything in that half reaction. We can then go on to the next step, which is balancing the 2 half reactions electrons to one another. So we see this is gaining 4 electrons and this is losing. And the whole point, remember, of redox is to get the electrons gained and lost so that they are equal. So that's not happening here. So I am going to need to do a multiple here. I'm going to need to bring our electrons to 12. So they're equally gained and lost. That means I'm going to need to apply a 3 all the way through here. So 3 times 2 is 6. 3 times 4 is, yay, 12. 3 times 1, well, that's just 3. Okay. And I need to get this 12, so this is going to be an applying of 4. So this is going to be 4. This is going to be 4. And then this is going to turn to 12. All right, so the green is me balancing between the 2 half reactions. The blue is balancing within that first half reaction. So kind of an important step to look at. Okay, now we can, before we add everything up, if we've got the electrons coming and going equally, we can cancel them out because that's the whole goal, is saying they're coming and going equally. It's not that they go away, we're just saying they're equal, so now we've done that. I don't need to write it in the final. I did it up above. So let's bring down all the reactants, everything to the left except the canceled out electrons. 6 mercury ions plus 4 solid irons yields, and this pen is kind of funny, yields 3 liquid mercuries plus 4 iron 3 plus. All right, well, okay, first of all, is everything balanced? Yes, there are 6 mercuries and there are 4 irons. Now let's check the charges. 6 times 2 is 12 plus on this side. This is neutral, so 12 plus is equal to 0 plus 12 plus. So everything's balanced. We do not need an acidic solution here. So let's go into an acidic solution example for you guys. Let's see, here it is. So in an acidic solution, that last step there, oxygens or the charges are not going to be balanced, but we go through everything like we do, and we don't apply the acidic balancing until the very end. It just saves us time. I also gave you this in its net form already. So let's go ahead. We need to decide what is reduced and what is oxidized. So let's assign oxidation states to the elements individually, and I'm going to go ahead and use green so you can see the difference. Oxygen is 2 negative. And we know this needs to add up to 2 negative, so that's negative 14. This should be 7 to get 14, but we're going to go ahead with 6 plus because that's 12. 12 plus negative 14 gives us negative 2. All right, so there's our chromium. That was a little more work. This is just the charge that we see. This is just the charge that we see, and same thing with iron. So wow, nice. Okay, well, those charges were found for us. So we notice oxygen is not even over here, so we know it's not oxidized or reduced. The only players that are oxidized and reduced are chromium and iron. Chromium is reduced, it goes 6 to 3. Iron is oxidized, it goes 2 to 3. So let's go ahead and start down that path. Cr2O7, 2 negative, yields Cr3 positive. Remember, this was a 6 positive. You might just need to note that to yourself. So how many electrons did it gain? 3. Okay. All right, now do not do oxidation yet. Let's look at the atom that was reduced. Oxygen, remember, is not reduced, so we're not going to worry about it. But we are going to notice there's 2 chromiums on this side and only 1. So, oh darn, I have to put a 2 here, which makes this a 6 electron. So just sometimes you see, if you look at example number 1, if you go back and watch the first video, not this one, you'll notice that that's an example of where you didn't have to bounce within a half reaction. This is an example you do. Okay, oxidized. Fe2 plus yields Fe3 plus, and that means it lost 1 electron. Okay, do I need to balance this half reaction? No, 1 iron and 1 iron. Okay, so it's good. All right, we're good there. So now I have to balance between reactions, so electrons coming in and leaving are equal. We notice they are not. If they were, we'd be good, but they're not. This is gaining 6 and this is losing 1. So I don't need to apply anything here. Our common multiple, we're going to get to 6. So I'm just going to multiply this whole thing by 6 throughout. And now the electrons coming and going are equal. And I can go ahead and add these up. I have, and I'm going to leave some room here on purpose, Cr2O7, 2 negative, dichromate ion, plus 6 iron 2s, gives me 2 chromium 3s, plus 6 iron 3 plus. All right, nice. All right, great. And we were hoping we were done, but we noticed a couple things right away. First thing, oxygen needs to be somewhere on the product side because we do need to have equal atoms coming and going. So when we are in an acidic solution, okay, we are using hydrogen ions to balance the charge and waters to balance the oxygen. Okay? So we can use those 2 things here, starting with water, to balance the oxygens. So there are 7 oxygens, so I need 7 waters. Okay, that gives me 7 oxygens over here if I distribute that. Okay, now I'm going to go through and I'm going to look at overall charges. So on this side, I have 1 dichromate at a 2 negative charge, and I have 6 times 2, or 12 positive. So I have a total of 10 positive on this side. So you've got to look at the overall charge and got to take your time figuring that out. I'm going to write it out in pencil for you. Here I have 2 3 positive, so I have a 6 positive added to 6 times 3. Holy freaking moly. 6 times 3 is 18 positives. So 24 positives. Wow. Okay. Well, that's not equal, is it? All right, so how many more positives? So the only thing I can play with is hydrogen plus. If it was a base, I could bring this down with an OH1 negative. But all I have is positive ones because I'm in an acidic solution. And hydrogen ions are the acid ion. That's what we mean. This has got hydrogen ions. This is an acid. So I'm going to go ahead and add 14 hydrogens. Okay, well that's nice. Plus 14 gives me 24 plus. Yeah, okay, we're equal on charge. Hot diggity dog. Most of you will start doing that mentally, but you might want to write it out like me while you're learning it. There's nothing wrong with that. Let's make these the hot ion. These are our, you don't have to, I just like to do the visual. Okay, so now we're going to see if things worked out. All right, we know the oxygens are equal. Let's check out, we know the chromiums are equal. Looks like our irons are equal. What about those the hydrogens? 14 and 14, nice, it's all balanced. So this is an example of an acidic redox where you have to add water to balance the oxygens. Water could be on either side, and you got to add hydrogen ion to balance the charges at the end after all your steps.